Thank you for having me. Delighted to be here. Today, I'll talk about the impact of dynamic lighting schedules. And by dynamic lighting schedules, I'll just define it up front. I mean, lighting that changes across the day, changes in terms of the spectral content, the intensity, and the timing of that sequence. So, for example, having blue enriched light during the day and then turning to blue depleted light and dimmer light in the evening. And specifically, we'll talk about the impact of that on helping the circadian system optimize its adaptation to changes in sleep-wake schedules associated with shift work. I have a few disclosures, but nothing directly related to the work that I'm presenting today. So we all know that shift work is associated with a whole host of different adverse health effects, uh, physiological effects, ranging from accidents and injuries, 54% increase in the odds of injury, mood and burnout, cardiometabolic impacts, increased risk of cardiovascular disease, effects on reproduction, especially in women, and then obviously inflammation as well. And what underlies these adverse physiological effects is primarily circadian misalignment. And we hear a lot about circadian, and I'll briefly touch on what is circadian. But basically, very simplistically, so in the aligned state, which is hopefully our typical daily state, we are normally sleeping at night when the body is promoting sleep based on its endogenous 24-hour timing. We are awake and working during the day. In contrast, in the misaligned state, so this would be in the case of shift workers, they're sleeping during the day when the sun is up and our body is actually indicating or promoting wakefulness, whereas they're working at night. So they're really fighting their sleep drive to stay awake and work. And so it's quite understandable that in that situation, the chances of making errors and accidents go up significantly. So in all the different physiological endpoints, health endpoints that do show adverse changes in response to shift work, you can see behind them all the different components are circadian regulated. So this is just an exemplary few studies that I've listed here, but this has been corroborated with different groups. If you look, for example, just at mood itself, you can see across the day, there's a circadian oscillation. So it's high at some times and it's lower at other times during the day. So when shift work induces this circadian misalignment, it disrupts the daily timing or the near 24-hour timing of these underlying physiological processes. And I'll just very quickly dive into the machinery, the clock machinery that regulates circadian rhythms. And so it all starts, the clock is a collection of neurons, about 6 to 10,000 in humans. And it is connected directly to the eye, so it receives the light input. There's a dedicated pathway, neural pathway, the retinohypothalamic tract, that carries that signal to the SCN. But importantly, the signal then reaches various other neural centers in the brain that regulates neuroendocrine responses, neurobehavioral responses, alertness, sleepiness. But it's also important to recognize that this signal doesn't necessarily have to go through the biological clock. It can go directly to other parts of the brain. For example, it goes to the habenula, which directly regulates mood, and other regions in the brain as well. So it can have direct impact. So light exposure can, at the same time, induce direct acute changes in physiological endpoints, and at the same time change the circadian timing of these physiological processes. And from the brain, it then travels down to peripheral organs as well. So when it comes to the circadian timing, it's composed of a molecular clock that is present in almost every cell in the body. And that clock, the clock in the brain and the clock in the peripheral organs, the molecular machinery is the same. But for light to reach the peripheral clocks, our current understanding is that it has to go through the central clock. And this is just a schematic of the central clock, which sits right above the optic chiasm in the mammals, including humans. We're not going to get into the details of all of this, but just to show a quick video, hopefully this plays. This is this clock oscillating every 24 hours. So each oscillation getting brighter and darker is 1 day. And this is gene expression in NDFCN in mice. And you can see how well it oscillates with a constant period across multiple days. Okay, so what's interesting, this is a seminal study that was done by Dr. Gene Duffy with Dr. Jack Seisler back in '96, more than 2 decades ago now. But this was a very elegant study to show that in humans, light exposure is the principal time cue, the main environmental stimulus that sets the timing of the central biological clock located in the suprachiasmatic nucleus that I just showed you. So they studied individuals in 4 different groups or 4 different conditions. And again, without getting into the full details in the interest of time, they contrasted dim lighting versus bright lighting. And by bright lighting, I mean 10,000 lux of white light, and dim lighting was less than 3 lux of white light. And individuals received these 2 different lighting conditions either during the early part of the night or the late part of the night in a simulated shift work protocol. So you can see the black bars are indicating sleep. And normally when they come into the lab, the first 3 days, they have sleep at night. And then they switch into a night shift protocol where they're sleeping during the day. And so they're either getting light in the early part of the night or the late part of the night. And what this shows is it's tracking the circadian clock, the time of the circadian clock in these individuals. And you can see that group 1 and 3 across the three assessment points, which is really over a period of 2 weeks, they don't really shift much. Whereas groups 2 and 4 shift a lot. Group 4 advances, group 2 delays. And that corresponds to this group and this group. So basically, if you get exposed to light in the early part of the night, you delay. If you get exposed to light in the late part of the night, then you typically advance. But again, the important point here is that their central clock advanced or delayed or shifted only when they were exposed to bright light, not when they were exposed to dim light. And this becomes important because we often think of, well, what about just changing the timing of sleep? Does that impact the circadian system? What about our feeding schedules? Does that impact the circadian system? And the clear answer from these sort of studies, and this has been replicated as well, is that no, for the central clock in humans, it really responds just to light. Even when you shift other things, because in this case, they were doing a simulated shift work, they did shift their sleep-wake timing, they did shift their meal schedules, their activity, but because they did not receive the bright light, the central clock did not shift. We and our others are doing a lot of work in terms of understanding how things like meal timing impact the circadian system. But what we're recognizing is that meal timing does not impact the central clock, it impacts peripheral clocks. But that's a whole different discussion, and maybe we can do a different presentation another day. For us, the central clock, which then synchronizes all the other peripheral clocks as well, the main principal cue for setting its time is light exposure. Okay, with that in mind, I'll jump into some dynamic lighting schedule work that we've been doing. I'll start off with a set of studies that we did in the lab under very controlled conditions. So we were trying to explore the impact of dynamic lighting schedules. Instead of, our typical exposure to light is very static, for artificial light at least. It's not changing in spectral composition, nor is it changing in intensity very much. But you can make the lighting more efficient and effective if you control or regulate the spectral and the intensity and the timing of that light exposure. So that's what we were trying to test. We did this in 44 healthy individuals, relatively young individuals. And the different types of lights that we used were primarily LED based or fluorescent based. And again, if there are questions, I can get into the details later on. But primarily there was a blue depleted dim lighting for pre-bedtime. And then for the daytime, we tried different types of blue enriched lighting at different intensities. And then it was the control lighting of the static fluorescent lighting. I'm not going to get into all the different protocols, but we tested 6 different protocols, which either advanced individuals or delayed individuals in their simulated shift work protocols. There were 4 consecutive night shifts in each of these protocols. And we even tried different things like giving an intermittent light exposure or introducing exercise along with light exposure, because there are often questions about, do you have to get exposed to blue enriched lighting to shift the clock for the entire duration that you're awake, or can you get strategically timed bouts of bright light exposure, and then the rest of the time you can just stay in indoor lighting? So we were trying all of that. And bottom line is, what we found was it's much easier to delay individuals than it is to induce advances, even when you're using optimized lighting with dynamic schedules. But within the delay protocol, we found that even with the addition of things like exercise, the ideal condition is when you have blue enriched bright lighting timed to induce the delay for the entire duration. So you want a continuous light exposure instead of intermittent or even room light exposure that we normally get. In other words, for the circadian system to adjust to the shifted schedule, a dynamic lighting schedule certainly facilitates that. And then this has consequences. So, for example, when we measured sleep using polysomnography, which is the gold standard objective method of measuring sleep, we see that indeed the ones who adapt more, which using the dynamic lighting schedule, have significantly better sleep. So almost an hour more sleep in the adapted individuals compared to the non-adapted individuals. And it changes sleep architecture as well, but primarily it's reducing the amount of wakefulness after falling asleep initially. So it's attenuating, circadian adaptation is attenuating sleep fragmentation, which has major cardiometabolic consequences and other health consequences as well. So taking it outside of the lab, we partnered up with NASA. We went into one of their research analog environments here at Johnson Space Center. And in this protocol, it wasn't really shift work necessarily, but we studied chronic variable sleep restriction, a model of chronic variable sleep restriction. What it essentially was that individuals would get 8 hours of sleep on the weekends, but on the weekdays they only got 5 hours of sleep for 5 consecutive days. So it's more similar to what the average individual faces in their regular lives when we are trying to cram our social schedules, our work schedules during the weekday, and so we tend to truncate our sleep or get less sleep during the weekdays, and then we try and catch up on the weekends. So that's what we were studying, the impact of that on the circadian system, and really contrasting what happens if you have a standard static lighting schedule during the day as compared to a dynamic lighting schedule that was blue enriched and bright during the day, and then 3 hours before bedtime it started to yellow and dim, and then right an hour before bedtime it was the dimmest and most blue depleted, or short wavelength depleted. And the impact of that is that, first of all, in the dynamic lighting schedule across the 45-day mission, the individuals, on average, when you look at the circadian clock, remained pretty stable. There was a delay, but importantly that even when individuals were delayed, on average, it was within their habitual sleep period. In contrast, when they're in the static lighting schedule, the typical indoor room lighting schedule, they delay such that across the 45-day mission that their circadian timing gets later and later, such that it's outside of their habitual sleep period. And this, when we looked at their sleep using diaries, in this case, sleep diaries, we found that in the dynamic lighting schedule, 93% of the sleep episodes were in the aligned state. Sleep was occurring at the optimal circadian phase. In contrast, in the standard lighting schedule, only 43% were aligned, the rest being misaligned. Clearly, a dynamic lighting schedule facilitates when you have a shifted sleep-wake schedule, either one that's in a shift work protocol or in our weekday-weekend transitions that we typically face. And we've extended this work. We've taken this all the way up to this International Space Station. They had to change their fluorescent lighting. They were getting LED lighting for energy efficiency. And then we collaborated and said, hang on a second, why don't we introduce dynamic lighting schedules there as well? We also tested the impact of dynamic lighting schedules in a care home facility. You may have seen me present this before. The primary outcome was falls. And the way we did this study, we looked at 4 different care homes, a pair of care homes within each parent company. And within each pair, one got an upgraded lighting system with dynamic lighting schedules, and the other remained as a static control. Looked at about 758 different residents with over 120,000 patient get days. And again, just to quickly illustrate that we went from a static lighting schedule to a dynamic lighting schedule that changes across the day. The primary outcome measure was falls. You've probably seen this before, so I'll just quickly go through it. The bottom line is that with the dynamic lighting schedule, there was a significant 43% reduction in the rate of falls with the dynamic lighting schedule. So the improvements that we see in sleep, depression, cognition do translate to harder outcomes such as falls, and specifically a reduction in the falls. And of course, for those who are interested, this is an independent report that was generated by PNNL. You can all access this, but there was, ranging between 60 to 75% improvement in energy efficiency with the dynamic lighting schedule as well. So just to summarize, I think we all recognize that circadian misalignment has a whole host of adverse physiological and health effects. There are different reasons for circadian misalignment, but for humans, the central clock is most sensitive to the light-dark schedule, and then optimizing the light-dark schedule primarily by implementing a dynamic lighting schedule that is in line with the sleep and circadian physiology that we know, does facilitate with circadian adaptation, and that has a lot of value proposition and returns on investment. But when you look at the different outcomes, reducing circadian misalignment, improving safety, productivity, etc. And so there's a higher ROI with the implementation of these dynamic lighting schedules in the work field. So I'll just finish up acknowledging my wonderful collaborators, the institutions that have supported this work, the funding agencies, and most importantly, all the different research participants and the technical staff that have facilitated this work. Thank you very much for your attention.
Shadab, thank you so much. That was absolutely fascinating. And there were a couple of questions that came through on the chat, and we'll just take a couple of minutes to ask you those, Shadab.
I'd like to pick up on a comment from Peter Thorns, which is about the random nature of human life, that we have our organized life pattern, like we go home, we go to work, but there's also other sorts of things happening in between. And do we have any sense of how that random pattern impacts on the data that you're collecting?
Yes. So that's a great question. Is certainly sleep in the circadian system is a multidimensional system. As much as we would like to say that light is the only thing that affects it, there are many other things from our random life that affects the system, even if it's indirect effects. So for example, this is what I say to a lot of individuals, that you can have the best lighting in your room, but if you happen to watch a movie or read a book with minimal light exposure, but it had disturbing content or it had very exciting content, once you turn off the lights, you did everything right, but once you've turned off the lights, you're going to wonder and think about that movie or that book. And that's going to impact how quickly you fall asleep or how well you sleep across the night. So yes, certainly our daily life events impact these systems independent of light or with light. And that's why we do both the control lab studies where all of this, the randomness is removed or controlled. And we also do field studies in applied settings to see if what we find in the lab translates to the field. By and large, they do. So the effects of dynamic lighting schedules and sleep and circadian informed lighting is robust enough to have benefits even with all the random changes that we experience in our daily life.